Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about Gauss's law. Now, in our last lesson we spent quite a bit of time doing derivations of electric fields due to continuous point charge distributions. Gauss's law is one of my favorite lessons in physics, because after we've gone through that really tough lesson and you survived it, we're going to show you a much simpler way to deal with a bunch of those situations. So our objectives. Number one, understand the relationship between electric field and electric flux. And we'll start by talking about what electric flux is. Secondly, calculate the flux of an electric field through a variety of surfaces. State and apply the relationship between flux and lines of force. State Gauss's law in integral form and apply it qualitatively. And apply Gauss's law to determine the electric field for planar, spherical, and cylindrically symmetric charge distributions. And that's going to be a big portion of the lesson. And almost without a doubt, that's going to be involved in at least one of the free response questions on your AP exam. And finally, apply Gauss's law to determine the charge density or total charge on a surface in terms of the electric field near that surface. So let's start off by talking about what is electric flux. Electric flux is the amount of electric field penetrating a surface. We'll give it the symbol, capital Phi. And if we have some random surface, whatever that surface happens to be, what we'll do is we'll define a small piece of that surface. And from that, coming out of it, perpendicular to it, we'll define a vector, dA, where the direction of dA, the area, is perpendicular to that surface. And assume we have some amount of electric field coming out of that surface as well, coming out through that area. The angle between these we'll call theta. Then this little bit of electric flux coming through that red portion, coming through our little bit of dA, we'll define as d phi, the flux, equals the electric field dotted with that area vector, dA, or E dA cosine theta if we're dealing with the magnitude, which implies then that the total flux is going to be the integral of that little bit of electric flux, which is going to be the integral over that entire area of all those little bits of E dot dA. You can almost think of this like airflow or rain on a cookie sheet. If you have a cookie sheet held flat and it's raining on it, the amount of rain that's hitting that cookie sheet would be equivalent to the flux. Now, really, flux goes through the surface. That doesn't work with rain in a cookie sheet, but maybe you get the idea. And if you start tilting it at different directions, different amounts of rain hit the cookie sheet or go through it. Wind through a grate, perhaps, something like that. So, what happens if you have a closed surface instead of just this open surface? Well, let's draw a closed surface. Something like that, and you'll have to try and picture that in 3D because my drawing skills are poor at best. Well, in this case, we could define some little piece over here as dA, or you could define, say, something over here as a dA. But once again, the total flux is going to be the integral over the closed surface, a shorthand notation, integral over a closed surface of E dot dA. So you're integrating over the entire thing to enclose it. And now by convention, normals to closed surfaces point from the inside to the outside. So total flux through a closed surface is positive if there is more flux from inside to outside. It's positive if there's more coming out than going in. If more is going in than coming out, then we would call that a negative flux. Just a convention as far as signs go. So let's take a look now at a point charge inside a hollow sphere to help us get an idea of how this Gauss's law thing really works. We'll place a point charge inside a hollow sphere of radius r. Let's draw ourselves a nice, happy little sphere of some radius, r. And at its center, we're going to put a point charge. Let's make it plus q. Pretty easy to see that electric field lines are going to be symmetric throughout, assuming I could draw a little bit better sphere. We could then say that the little bit of electric flux through some little piece of this, dA, and let me define that dA here, is going to be equal to the electric field dotted with dA, which, as we said previously, is just E dA cosine theta. But if it's a point charge inside a hollow sphere, anywhere the electric field goes through that sphere, it's going to be perpendicular, uniformly around the entire sphere. So that means that theta, everywhere, the angle between those two, is going to be 0, so cosine of theta is going to be equal to 1. Therefore, the differential of that total flux, that little bit of flux, is going to be just E dA. And our total flux, then, is going to be the integral of all those little bits of flux, or the integral over this closed surface around the entire sphere of E dA. But since it's a point charge inside the center of a sphere, the electric field is going to be the same everywhere as you go around that entire area. So for the purposes of this problem, E is a constant. So the E comes out of the integral sign, E integral over the closed surface of dA. But the integral over the closed surface of that differential of area as you go around the entire surface is just going to give you that entire area. So that becomes EA. And as you know, the area of a sphere is equal to 4 pi r squared. So we could write then that the total flux is going to be equal to E times 4 pi r squared. Even further, though, we know the electric field. We just spent a whole lesson on it. The electric field due to that point charge is equal to Q over 4 pi epsilon naught r squared in the direction of r hat, heading out from that point charge. So we could then write the flux as being equal to, we've got our 4 pi r squared times our electric field, capital Q, over 4 pi epsilon naught r squared. And all of that then must be equal to, let's see, 4 pi, r squared, it's equal to Q over epsilon naught. Simplifies very nicely, which implies then that the total flux is equal to the integral over the closed surface of E dot dA, which was equal to the total charge enclosed by our sphere divided by epsilon naught. And there's a poor man's derivation of what we're going to call Gauss's law, the first of Maxwell's 4 equations, which form the backbone of this entire E&M course. Gauss's law, gotta know it, frontwards, backwards, upside down, underwater. The total flux is the integral over the closed surface of E dot dA, which is the total charge enclosed by your surface divided by epsilon naught. Looking at this in a little bit more detail, what is this law good for? It's extremely useful for finding the electric field due to charge distributions in cases where you have symmetry, and you need specifically one of 3 types of symmetry. You need spherical symmetry, planar symmetry, or cylindrical symmetry for this to be a very useful law. Gauss's law always holds. It's always true. However, it's really only useful for the most part in these cases. And again, what it states, the total flux is the integral over the closed surface of E dot dA, which is the total charge enclosed by that surface, divided by epsilon 0, that constant. Let's do some examples. Find the electric field inside and outside a thin hollow shell of uniformly distributed charge Q. All right, well, let's see if we can't draw this first. Find the electric field inside and outside a thin hollow shell of uniformly distributed charge Q. So there's our shell of charge with some amount Q. Now, what we're going to do is we're going to choose a Gaussian surface. Envision this imaginary surface, closed surface. In this case, it's going to be a sphere to give us the most possible symmetry. First, we're going to do that inside the shell, and then we're going to do it outside the shell, wherever we want to know the electric field strength. By symmetry, the electric field at all points on this Gaussian surface, on this Gaussian sphere, must be the same and must point radially in or out. So as we do this, let's start with inside. Let's look inside this sphere. We'll define a Gaussian sphere here in green, this mental sphere that we've made up to help us solve the problem. And we'll say that it's at some radius, which we'll call Ri, which is inside the radius of our shell of charge there in blue with radius capital R. So here's our Gaussian surface in green. And we're looking for the electric field inside. So where Ri is less than R. And let's even spell that out. Ri is less than R for this analysis. Once we do that, we can say that the integral over the closed surface of E dot dA equals Q enclosed by our Gaussian surface divided by epsilon naught. Gauss's law. We start off by writing it. Then we also know that the area over here of our Gaussian surface is just going to be 4 pi Ri squared, because we picked another sphere inside that shell of charge, so we'd have as much symmetry as possible. So then we could state that the left-hand side, E is constant everywhere. The integral of dA is just going to be the area. Left-hand side becomes EA equals Q enclosed over epsilon naught. Note, we didn't have to do any real integration. When you're using Gauss's law, vast majority of the time, if you have to do any real integration over here, you probably didn't pick the greatest surface. EA equals Q enclosed over epsilon naught, which implies then that E times our area, 4 pi Ri squared, equals the charge enclosed divided by epsilon naught. Or we could say then that E equals charge enclosed over 4 pi epsilon naught Ri squared. What makes this one especially easy, though, is the charge enclosed by our Gaussian sphere is 0. All the charge is outside in this blue shell of charge. There's nothing inside our Gaussian sphere. Q enclosed equals 0. Therefore, the electric field equals 0 inside that hollow shell of charge. Gauss's law to find the electric field inside where it is 0 everywhere. Let's take a look at the second area. Now we're going to look when we're looking outside that hollow shell of charge. So instead of looking at the green one, let's take a look at this purple one. We'll set a Gaussian surface, another sphere, a hollow shell, I should say, outside our shell of charge. And why don't we call this one RO? Has radius RO. So now we're looking where RO is greater than capital R, or outside that hollow shell of charge. We'll start off by writing Gauss's law again. Integral over the closed surface of E dot dA equals the charge enclosed divided by epsilon naught. Same thing again, and same derivation as well. E is a constant everywhere because we chose our Gaussian surface very carefully. The integral over the closed surface of dA is just going to be A. So then EA equals Q enclosed over epsilon naught, where again this area is the area of your Gaussian sphere. The area of that sphere is going to be 4 pi RO squared equals Q enclosed over epsilon naught, which implies then that the electric field is going to be our Q enclosed over 4 pi epsilon naught R0 squared. So the total charge enclosed is plus Q, so that's going to be Q divided by 4 pi epsilon naught R0 squared for any R that is an RO that's outside this hollow shell of charge. Wow, this is the same as if all the charge was placed at a point in the center of the sphere. You could treat it like it's a point charge once you're outside. It doesn't matter what shape it is, as long as you can use Gauss's law on it. This could be any amount of charge, any size diameter shell. As long as you are outside it, you can treat it all as if all of that charge was condensed at a single point inside at the center of that shell. See how powerful this is, how much slicker this is? You can just see the beauty and all the symmetry of the math as you do these sorts of problems. And we'll go through a couple more examples to help clarify it. But let's make a graph quickly of the electric field versus radius, just to help finish this one off. So there's our radius R. There's our electric field. And what we have is inside that value of R. Let's make this capital R. I'll write it in blue even, just so it corresponds to our shell of charge here. There's the radius of our shell of charge. Inside that, the electric field is 0. And outside that, it's Q over 4 pi epsilon naught R0 squared. So what we have is a discontinuity where we've got something like this, where that is proportional to alpha sign, fish sign, whatever you want to call it, is proportional to 1 over R squared as long as you're outside R. So there's your graph of electric field versus radial distance. You can use Gauss's law to help you find these so quickly and so easily. Let's do another example. Find the electric field due to an infinite plane of uniform charge density sigma. All right, well, we've got an infinite plane. Let's draw that here. Our plane of charge that goes on and on and on, and we've given it some surface charge density sigma, which is total charge divided by area. Since it's infinite, we can't know the total charge or the area, so we'll find the ratio of those and define that as sigma. To choose our Gaussian surface, we got to be smart about this, and having done these sorts of things before, I know that a good way to do this is to pick a cylinder. So I'm going to pick a cylinder. Think of it almost as a soda can, centered on that sphere, on that plane. There's the top, and it also extends by the same amount underneath. So there's our Gaussian surface, a cylinder. And we'll set it so that it is some distance d above and d below that infinite plane. So by symmetry, the electric field at all points on the cylinder must point perpendicular to the plane through the caps of the cylinder. And on the sides, it should be pretty easy to see by symmetry. Everything's going to cancel out. So we're only going to end up having to worry about these caps on our cylinder. But let's go through that step by step. Start by writing Gauss's law. The integral over the closed surface of E dot dA is equal to our enclosed charge divided by epsilon naught. Which implies then, since we know sigma is Q over A, and Q equals sigma A, we can write then, well, the left-hand side, this total flux, I'm going to break up into pieces. I'm going to take a look at the flux through the top, the flux through the sides, and the flux through the bottom cap. So that's the flux through the top plus the electric flux through the bottom plus the total electric flux through the sides to give me my total, which is this left-hand side, and that must be equal to our charge enclosed, which is sigma times A, where that is going to be our A, divided by epsilon 0. And of course, by symmetry, we can look and see that the flux through the sides of this are all going to cancel out. So the total flux through the sides is going to be 0. So we can say then that the flux through the top plus the electric flux through the bottom must equal sigma A over epsilon naught. All right, next up, the flux through the top and the flux through the bottom must be the same, right? Because they're symmetric. This one's pointing down, this one's pointing up. We're worried about magnitudes for the time being. So the flux through the top equals the flux through the bottom, which, by the way, has to be the electric field at that point times the area. So that's equal to EA. So flux through the top EA plus flux through the bottom EA gives us 2 EA must equal sigma A over epsilon naught, or solving for the electric field then, the electric field just equals sigma over 2 epsilon naught. There's no dependence whatsoever on D. And we've seen this before when we talk about infinite planes, infinite lines. It doesn't matter. Since it's infinite, really the only thing you're worried about is that surface charge density. How much simpler is that than the derivation that we did with that disk that we grew bigger and bigger and bigger in the last lesson to figure out the electric field due to an infinite plane? Much slicker derivation right here using Gauss's law. And let's do a graph of the electric field versus distance again, just so that we're consistent. There's D, there's our electric field, and as there is no dependence on D, our graph looks like a nice straight line at sigma over 2 epsilon naught. Very good. Let's see if we can't extend this a little further and talk about parallel plates. Find the electric field outside and between two oppositely charged parallel planes or plates. So let's draw our plates first. We'll draw a top plate. We'll draw a bottom plate. We'll say that this one has charge density plus sigma, so this one must have minus sigma as its charge density. Now what we're going to do is we're going to look at the electric field due to the different plates in different regions. So if I look at the electric field due to just the top one, the plus sigma, over here on the left, the electric field due to the top plate must be going away, since that's a positive charge. And on this side of it, it must be going away. And over here, we're still looking at the electric field just due to this one, so it must be going away. And everywhere, the magnitude of that is sigma over 2 epsilon naught. Now let's take a look at the electric field due to just the bottom plate in these regions. As a negative charge density, it's going to have the field lines going toward it. So up in this region, we have sigma over 2 epsilon naught toward it. Same thing here, still toward the bottom plate. Again, we're looking at just the electric field due to the bottom plate for now. And down here, we're going toward that negatively charged plate. So when we put these together, if we want to find the total or the net electric field, up above the two plates, we have sigma over 2 epsilon naught up and sigma over 2 epsilon naught down, which gives us an electric field equal to 0 there. In between the two plates, we have sigma over 2 epsilon naught down due to the top plate, sigma over 2 epsilon naught down due to the bottom plate. So our total electric field here is going to be sigma over epsilon naught headed down. And at the very bottom again, we have sigma over 2 epsilon naught down, sigma over 2 epsilon naught up, so the electric field is 0. So what we really find after all of this is that between the parallel plates, above the plates, no electric field, below the plates, no electric field, and between the plates, sigma over epsilon naught going from the positive to the negative. Now, it's important to note that this is not accurate when you get near the ends of real plates. If it's an infinite plane of charge, absolutely works great. But when you get to the edges, you actually get some sort of fringing effects like this. So you've got to have very big plates and either neglect the edges or have infinite planes for this to make sense. But it's a pretty good approximation for most plates, especially in the region not near the very edges of those plates. Let's take a look at another example. Find the electric field strength at a distance r from an infinitely long, uniformly charged wire of linear charge density lambda. All right, so we've done wires before. As I recall, we got into quite a bit of math. Going to be quite a bit simpler here using Gauss's law. So let's start by drawing our wire. And we're going to give it some linear charge density lambda. Now we've got to pick a Gaussian surface that's going to give us the most possible symmetry. And in this case, for a wire, what I'm going to choose is a cylinder that is centered on that wire. So let's choose a cylinder, something like that, for our Gaussian surface. And what's nice there is we've got a cap on this end, a cap on this end, but just by observation, we can see by symmetry that those are going to completely cancel out, and all we're going to have to worry about is the pieces going through the sides of our cylinder, through the edges of our can, not the top or the bottom. So we'll start off by writing Gauss's law again. Integral over the closed surface of E dot dA equals the total enclosed charge, the charge enclosed by our Gaussian surface, divided by epsilon 0. This is the total flux, but we're going to break that flux up into a piece through the left cap, a piece through the right cap, and a piece through the sides, or I'm just going to write that as the cylinder portion for our flux, must equal Q enclosed over epsilon naught. And as we just mentioned, by symmetry, we can state that the flux through the left plus the flux through the right must equal 0. So all we have to worry about is the flux through the sides of our cylinder, what I'm calling the cylinder portion, equals the total enclosed charge through our cylinder divided by epsilon naught. Now, to find the flux through our cylinder, first thing we have to realize is because it has the wire in the middle, the electric field is going to be the same anywhere on the edges of that cylinder, anywhere around it. That nice piece of symmetry again, as we chose our Gaussian surface very wisely. We need to know the area of that, however. If we have the edges of a can, to find the area of it, what we really need to do is think about cutting it and spreading it out. So we've got our cylinder, we've got to spread it out somehow. What would the dimensions of that be once you've spread it out? Well, the way we're going to do that is we'll say that the flux through the cylinder is going to be, well, if the radius of the top of the cap is 2 pi r and we cut it, that's going to be one dimension of our rectangle we get when we spread out that can piece. So that'll be 2 pi r. And the other dimension is going to be some L that we haven't defined yet, the length of our can. L. So we've got that, and we have to multiply that all, of course, by our electric field to get the total flux. So there's our EA, which is the flux through that. So we can then write that we have our 2 pi RL times our electric field equals our enclosed charge divided by epsilon naught. Now we'll go back to our linear charge density lambda, which we know lambda is total charge divided by length. So then our Q enclosed, the amount of charge enclosed by our cylinder, is just going to be the linear charge density times this length, L. So then we have on the left-hand side 2 pi r L times our electric field equals Q enclosed on the right, lambda L divided by epsilon naught. Or solving for the electric field, E equals lambda over 2 pi epsilon naught R. Same as the answer we reached using that point charge summation in the previous lesson, but so much simpler, easier, slicker, quicker, and much, much, much more intuitive too. Gauss's law is a very, very powerful tool. Let's take a look at some old AP questions to hone our skills here. And we'll start off by looking at the 2008 E&M exam, free response number 1. And you can look that up on Google, College Board website. It's available for you to download, to print out. Here's a link to it currently. I'd highly recommend taking a minute, printing it out, and taking a couple seconds and seeing if you can't solve it on your own before you check the answers. And if you get stuck, that's perfectly fine. Then come back to the video and play along with it. And if you got the whole thing, just check your answers as you go through and see what you got right and what might need more work. Use this as a practice opportunity. So, in this question, we're starting off with a metal sphere that of radius A containing a charge plus Q, and it's surrounded by an uncharged concentric metallic shell of inner radius B and outer radius C. And it wants us to first determine the induced charge on the inner surface of the metallic shell. So the way I'd start to do that is looking at part A here. We have some solid, positively charged plus Q piece there, and outside of that we have another conducting shell. Got plus Q on the middle, and out here we're asked to find what is the charge on the inner surface of this shell. So over here at this radius that they call B. That's B, and they're defining that as A. Well, the way I would do that to begin with is I would first choose a Gaussian surface that is inside this shell and then apply Gauss's law. So I'm going to make a shell here that's actually runs through the middle of that conducting shell. So there's my Gaussian surface, that sphere there in purple. Then the integral over the closed surface of E dot dA is the enclosed charge divided by epsilon 0. Now, to do this next step, you probably need to have seen this before, either in a previous physics class. You have to know that the electric field inside a conductor is 0. When you know that the electric field inside a conductor is 0, this becomes very simple. And we'll get to that in a later lesson, but if you've seen that in a previous algebra-based physics course, that'd be a great start here. Once you know that, then you can say, well, the left-hand side, if we know the electric field is 0, the left-hand side, 0 dotted with something must be 0, is equal to Q enclosed divided by epsilon naught. Therefore, Q enclosed by our Gaussian surface must be 0. And Q enclosed includes plus Q from our inner sphere plus, let's call it QB, whatever we have on the inner surface of this shell, must be equal to 0. And if Q plus QB equals 0, that implies then to me that QB must be equal to negative Q. So our answer is negative Q. If you have plus Q here on the outside of this sphere, you must have a negative Q charge on the inside there, using Gauss's law. The trick, knowing where to put your Gaussian surface. Let's take a look at the second part there. Find the induced charge on the outer surface of the metallic shell. And to do that, I'm going to choose a Gaussian surface now that is outside that shell. I'm going to use that red Gaussian surface for part 2. The integral now over the closed surface of E dot dA, which is Q enclosed over epsilon naught, always starting by writing Gauss's law, must be equal to, well, the total enclosed charge must be plus Q. We know that because it says this is neutral in the hole, and that's your positive plus Q. So once we do that, we can realize that, well, Q enclosed equals, we've got our QA, which we called plus Q over there. We have our QB, and we now have our QC, which is what we'll call the charge on the outside of that sphere. So this implies then that our plus Q, our total enclosed charge, Q enclosed plus Q, must be equal to, well, we know QA is plus Q, we know QB is minus Q, plus whatever QC is. Well, the only way that'll work, if we have plus Q total, plus Q and minus Q is going to be 0, that implies then that QC must be equal to plus Q. So the charge on the outside here must be plus Q, which only makes sense by the law of conservation of charge. If we said we had minus Q on this inner surface and the whole thing's neutral, we must have plus Q on that outer surface. So there's how we would do part A. Let's take a look and slide over to doing part B now. And it asks us to determine expressions for the magnitude of the electric field as a function of radial distance for different regions. And for the first region, and I'll call region I, we have R is less than A. So we are inside that inner sphere. Well, in order to do these problems, I'm first going to define now a volume charge density, where rho equals Q over V equals Q over, you know what, I'm not sure I'm going to need that because we've got conductors, 4 pi A cubed. I'll define it, but I'm not sure we're going to need it now that I think about it. So let's take a look here. For R less than A, Gauss's law, integral over the closed surface, E dot dA equals the total charge enclosed divided by epsilon naught. Well, left-hand side just becomes E times the area. The right-hand side is our charge enclosed, which is 0. Therefore, we can state that the electric field is 0 inside that metal sphere, which of course we knew because we already said just a few moments ago that the electric field inside a conductor must be 0. All right, well, we proved it. Let's move on to part 2. Now we're looking in that region between the solid sphere and that hollow conducting shell. Or that solid conducting shell, I should say. So here we have R between A and B in that diagram. Well, now the integral over the closed surface of E dot dA is Q enclosed over epsilon naught. Again, choosing a Gaussian surface that's in that region, which implies that EA, which is going to be E times 4 pi R squared, where R is between A and B, must equal our total charge enclosed plus Q divided by epsilon naught. Therefore, the electric field is just going to be Q over 4 pi epsilon naught R squared in that region. Just like it was a point charge. Moving on to part 3. Now we have R between B and C, or again, we are looking inside that region. Oh, let me draw a picture of it just to make it clear. There's our solid sphere. Here's our conducting sphere. Now we want our R somewhere in this region there in red. Well, we can do that easily in a couple ways. We know already, since this is plus Q here and minus Q on this surface, our total enclosed charge is 0. Therefore, the electric field is going to come out to be 0. Or once again, we're inside a conductor at this point. electric field must be 0. Straightforward. And part 4. Now what we're going to do is look for R greater than C. So we're in some region out here outside the entire object, the entire setup. Well, in this case, we'll start off with Gauss's law again. Integral over the closed surface of E dot dA equals the enclosed charge divided by epsilon 0. Left-hand side becomes the electric field times the area, E times 4 pi r squared. Our total charge enclosed is just plus Q. Therefore, the electric field again is Q over 4 pi epsilon naught r squared. And again, we're treating the entire thing, as long as you're outside of that, outside of all those pieces, as if the entire charge was concentrated at a single point. Same answer. So again, the power of Gauss's law. All right, now it wants us to do a graph of the electric field as a function of distance, which should be pretty straightforward because we just figured out all of the different pieces analytically. So let's draw our graph here. There's our R. There's our electric field. And let's make a couple marks here for A, B, and C, just to help us delimit where things are in the graph. A, B, and C. Well, we already know between 0 and A the electric field is 0, and between B and C the electric field is 0. Those regions where you're inside the conductor, electric field 0 inside a conductor. And when we are between A and B, we are proportional to 1 over r squared. And when we're outside of C, we're again proportional to 1 over r squared. So a fairly straightforward, simple graph. That's part C of the question. And part D, if this is your first physics course, could be a little bit tricky. If you've had algebra-based physics before, then you've probably had this before and it's a fair question. Either way, it's fair by the time you finish the entire course sequence. So we're given an electron of mass me, it's carrying a charge minus e, is released from rest a very large distance from the spheres. Find the expression for the speed of that particle at a distance 10r from the center of the spheres. And they really meant to say 10c from the center of the spheres. So, what's helpful to know here is that the electrical potential energy, due to those point charges, is 1 over 4 pi epsilon naught times the one charge times the other charge divided by r. That's the piece that you probably have to know already. So I would do this from a conservation of energy perspective as a fairly easy way to solve this problem, knowing that the kinetic energy plus the potential energy is going to remain constant. Because you're starting a very large distance from the spheres, we're going to say that's our potential energy level of, well, from rest, a large distance. If it's at rest, kinetic energy is 0, potential is 0. Therefore, the kinetic energy is going to be 1/2 me v squared, and that's got to be equal to the potential energy, Q, times the charge, E, over 4 pi epsilon naught times our distance, 10c. So now it's just an exercise in algebra to find the velocity. V squared then is going to be equal to, now let's see, if we've got the 2 there, we're going to have Q times E over 2 pi epsilon naught me times 10c. Therefore, V itself is going to be equal to the square root of that. QE over 2 times 10 is going to be 20 pi epsilon naught me c square root. All right, so D might be a little tricky if you haven't gotten to the potential energy piece in electrostatics yet. We'll get there in a couple lectures. But the rest of it, pretty straightforward application and great practice for Gauss's law. All right, let's do one more free response problem here. This one from the 2011 test, free response number 1, that was kind of an interesting take on Gauss's law and whether you really understand how this law works, and also a bit of close reading. So in this problem, they start off by asking you to use Gauss's law to prove that the electric field inside a spherical shell with the uniform surface charge density sigma on its outside surface and no charge anywhere else inside is 0. And describe the Gaussian surface you would use. We've been doing that for a while now. So let's take a look. Here we'll call this A. If we use a spherical shell that's inside the charged shell, as our Gaussian surface, well, then we have some charge sigma here in our Gaussian surface inside it. The integral over the closed surface, E dot dA equals Q enclosed over epsilon naught. And the Q enclosed inside there is 0. So since Q enclosed equals 0, we can say that E times the area, 4 pi r squared, equals 0. Therefore, E equals 0. Nice, quick proof. Done. Now for part B, it says the charges are now redistributed so that the surface charge density here is no longer uniform. Is the electric field still 0 everywhere inside the shell? And the answer, of course, is no. When you do that, without the symmetry of charges to cancel each other out, there can be an internal electric field. Gauss's law still holds, but it's not the same everywhere. So using Gauss's law isn't overly helpful to you in this point for determining an electric field. So I would write something like no, without the symmetry of charges to cancel each other out, you may have an internal electric field. So something like that should work. Now they change it up. Here's where they throw you the curveball, something you might not have seen before, which makes it a really great question. They give you a small conducting sphere with charge plus Q with the center that's at the corner of a cubical surface. And again, if you haven't downloaded and look at the question, make sure you do this, otherwise this isn't going to make any sense. For which faces of the surface, if any, is the electric flux through the face equal to 0? Well, as you look at the diagram, the only place the electric flux is going to be 0 is when the field lines are running parallel to the surfaces. And of the 6 surfaces on the cube, 3 surfaces are going to be parallel, are going to be touching that point, so you have electric field lines parallel to them, so no flux through those surfaces. And those ones would be ADEH, ABCD, and ABGH. And I think it asks you to explain your reasoning. Something like field lines run parallel to these surfaces. Therefore, no flux through these surfaces. All right, moving on. Let's take a look at D. At which corners of the surface does the electric field have the least magnitude? Oh, that could be really tricky if you don't read the question very, very carefully. At which corner do you have the least magnitude of electric field? And you have to realize at this point that they're talking about a small conducting sphere whose center is at the corner A. Conducting sphere. Inside a conductor, the electric field is 0. So point A, which is inside the conductor, has to have 0 electric field. So I would state that A is inside the conducting sphere, and the electric field is 0 inside a conductor at equilibrium. Kind of a trick question there if you haven't read it very, very carefully. All right, let's take a look at part E. Find the electric field strength at the positions you indicated in part D. Well, we just did that. And I think they're trying to throw you off again by giving you all these fundamental constants. You don't need them. You already know inside a conductor, E equals 0. So E at point A equals 0. Done. And finally, last part of the question and last part of this lesson. Given that 1/8 of the sphere at point A is inside the surface, find the electric flux through face CDEF. Well, Gauss's law, integral over the closed surface of E dot dA, is equal to Q enclosed over epsilon naught. But now our Q enclosed is Q divided by 8 because only 1/8 of that sphere is inside our cube. So Q enclosed is Q over 8, so that's Q over 8 epsilon naught. Now, by symmetry, we have 3 faces of the cube that have flux running through them. They're all symmetric. They all have the same orientation, the same distance with respect to that point A. Therefore, each one's going to get 1/3 of the total flux. So that's going to be 1/3 of Q over 8 epsilon naught, or I would say the flux through each one is going to be Q over 24 epsilon naught. All right, hopefully that gets you a good start on Gauss's law, an extremely important part of the course. If you struggled with it, please take your time, go back, do some practice problems. You are really going to need this for success in the APC E&M exam. Thank you so much for watching Educator.com. We'll see you again real soon. Make it a great day.